Hello, my name is Wyatt Kirby, and today I'll be breaking down how to make a counting circuit. I'll be doing this by explaining the different mini circuits inside and explaining the chip functions. The main things that we use to make up the counting circuit are the button input, the NAND gate oscillator, the decade counter, the decimal counting binary up-down counter, the binary counting decimal decoder, or the 4511 chip, and a 7-segment display. When all combined, the counting circuit is capable of counting in both directions, up and down, in numerical order. However, it can only count to 10, and that's why we are able to use a 7-segment display which only displays digits 0 through 9. The button input is the first circuit built in order to make a counting circuit. This is done through a 4011 logic gate, and when combined with the next circuit, the NAND gate oscillator, it creates a clock signal. We can define a clock signal as a particular type of signal that oscillates between a high and low state. This will be demonstrated in the next circuit. The NAND gate oscillator's primary function is to create a clock signal when paired with the button input. The NAND gate oscillator uses the same chip as the button input, the 4001. This creates a clock signal, which, as shown on our circuit, can create a flashing light because current is constantly being differentiated between a high and a low. Now for the decade counter. With this, we can remove our test LED and bring our final result from the previous two circuits over to this one. The 4017 is the primary component in this circuit. This chip uses our clock signal to create a pulse that counts to 10 through digits 0 to 9. This is essentially the part of the circuit that makes it count. Next is the decimal counting binary up-down counter. This circuit can be accomplished by using a 4510 or a 4516. This paired with a single pole double throw slide switch can cause the circuit to count backwards and forwards, both in numerical order. These are all of the 4-bit binary values used in this circuit. The binary counting decimal decoder is a 4511 chip, and it is used in our final prototype. This chip converts the binary we have created into real numbers. These real numbers are then sent to the 7-segment display to display. As you can see, all outputs on the 4511 chip are all on the same side of the chip, which makes wiring very easy. The final part of the breadboard prototype is the 7-segment display. The 7-segment display is a combination of 4 LEDs, which each receive an output from the 4511 chip. The 7 separate LEDs in the 7-segment display light up based on the information we have created to create the digits 0 to 9. Now we can begin soldering onto the final PCB. However, we need to add a number of new components first. First, 2 resistor networks for the 7-segment display. This makes the wiring much easier, and it makes the final PCB look much cleaner. Next, a term block. This is how we get power onto our PCB. And next, 1 14-pin chip seat and 3 16-pin chip seats. These prevent our chips from heating up. Congratulations, you have now finished soldering your final PCB. It is now time to add this PCB into a sleek 3D printed case. Since the battery will be directly under the PCB, touching the soldered leads, it may overheat your chips, which is why you must wrap it in electrical tape. Congratulations, you have now successfully built a counting circuit. Thank you so much for watching and have a wonderful day.